So we'll just go over more of theoretical, not practical, but I think I have a MATLAB example at the end of these slides. But we'll go over the multi-fare problem. So it's a common problem. It's actually very common, but it's very common in the airlines.
Yeah.
So we'll go over, like we have a certain number of seats on an airplane, and we're going to let so many seats go at a lower price, and then the remainder go at a higher price. And then the question is, what we want to focus on is how many seats should we reserve for the higher price?
Correct.
And marginal analysis, has that ever come up in other classes, the phrase marginal analysis in your business classes?
I don't remember, I don't
Okay,
know.
but it's just basically saying if we would have changed our number, so let's say for example we had an airplane with 100 seats and we decided to let 40 go at the lower price and save 60. Then we ask ourselves, what if we made it from 60 to 59? Does it make things better or worse?
Okay.
And if it makes things better, we'll do it. If it makes things worse, we won't.
So marginal analysis is like a small change.
Right. How
to
much?
The,
Right. One unit of change. See how that affects our overall situation, which kind of leads to this famous Littlewood's rule, and then some MATLAB code that kind of follows the example. So the overall example is basically we have like I'll use the airplane as an example, but this really applies to anything, making donuts or anything like that. We have a finite capacity C. So let's just say, I think it's easier to follow, we'll say an airplane with 100 seats, even though that doesn't really make sense. It's always like rows of 6, so 6 times something, but 600 isn't divisible. But anyway, let's say we have a capacity of 100. We have a finite sales horizon. So a horizon is how far you can see. So let's say the airplane leaves next Friday, so we can only sell, let's say a month from Friday. So we can only sell seats before the flight leaves. Once the flight leaves, we can no longer sell seats. The plane's up in the air. So there's a finite time where we can sell things. And in these examples, it makes it a little bit simpler to have zero storage value. In other words, sending out empty seats doesn't have any value, like saying, oh, it's less gas because it's less weight or something like that. So an empty seat is just considered a total loss, right? There's no advantage to that. And then we usually do this through a reservation system. So let's say we have a 2-market system, and we realize we could expand this to more markets, but let's say we're going to use the convention that the lower number class is the higher price. So like class 1 is maybe the business class, people will pay the most. And we'll just say class 2 might be like vacationers, so people who are willing to book far in advance if they can pay less money. And we'll use the convention, the price of class 1 is always higher than the price of class 2. And then this is sometimes the demand for each of those classes, we're going to make the assumption here, because it kind of makes our models a little bit easier to do. But we can remove this assumption, it won't make the problem that much harder, but we're going to say that the amount of demand at the higher paying class is independent of the demand at the lower paying class, which in the real world is not 100% true. Like, so if somebody, have you ever called up an airlines and wanted to book like a low fare, and they say, well, we don't have any more of the low fare seats, however we have the higher fare one, and you said, okay, I'll take the higher one?
I've never called to make a reservation. It's always been online, except when I do the India travel.
Okay.
And we have like a travel agent whom we call, and she keeps quoting different prices for different dates.
Okay, but have you ever been in your mind, you thought you were in one of these classes, and then it wasn't available, so you said, all right, I'll pay the extra?
Extra, yeah.
Okay, so that's kind of where the two demands overlap. Like, in other words, if we made the number of seats that are going at the lower fare smaller, it might cause the people who were originally planning to go on vacation and pay a lower fare say, all right, I'll jump to the higher one. So they're kind of like making one smaller makes the other one bigger. But in our example, we're going to say they're independent. We're just going to say, we'll roll the dice to see how many come up in class 2, and then roll the dice again. So, okay. So the two extreme strategies. So now we have we have our two fares, and there's two things we can do. We can say we're going to sell only the full fare, only the high price one, and just see who comes. If the plane fills up, great. But if the plane goes out with 90% of the seats empty, we might have been better off selling lower fare ones. Okay, so then the question is, how much money would we get if we use that system? So the expected revenue would be the high price, like maybe $699, times the expected number of people who will show up. But it could be, so let's say for example the plane holds 100 seats, and let's say 120 people want to buy the seat. Well, we can only sell 100 because we only have 100 seats. If 80 people come, but the plane can hold 100, well then we're only going to get 80 sales. So we're going to take the price times whatever's the minimum of the demand, the number of people show up, and the number of seats on the plane. Whatever's the smaller of those two numbers. We'll multiply that by the price, and that's how much money we can expect to get. The other extreme would be to let as many seats as we want, let's say a month in advance of the flight leaving, we could say let as many seats as we want go at the lower price, and then on a so let's say our rules were something like if you book 21 days in advance you get the lower price, and then within 21 days you have to pay the higher price, but we'll let as many seats go for sale. So it is possible they could all be taken up at the lower price. So that's the other extreme. Now how much money would we expect to see? So it's kind of good to know these formulas, because then we're just going to add and change things to get a mixture of the two. So we would take the amount that comes in at whatever the lower price is. So let's say, for example, our prices were $699 and $299. So it would be the $299 price, and then how many of those do we sell? Well, it's going to be the smaller, just the same as up here. However many people show up at price level 2, and the capacity of the plane. Whichever one of those two numbers is smaller, we'll take the smaller one. That's how many we sell at the lower price. Now, how many do we sell at the higher price? Well, it would be the higher price times, now we have to say, of all the seats left over after the lower price ones ate up all those seats, whatever those are left over, or the amount that was demanded, whichever is lower, right? So we would take the minimum of the demand at the higher price, or the number of seats on the plane minus all the people, because we're selling all of them. Whichever one of these two is the lower number. Now this notation, I don't know if you've ever seen this one, it's always described as positive part. It looks like it's raised to the power of plus. But they always say like C minus D2 positive part. That's the way it's described. And I think that's a confusing name for it, because what it means is we take C and we minus D2, and if this number is positive, we use that value. And if this number is negative, we use 0 instead. But they refer to it as positive parts. It should be something like 0 if not positive. Might have been the best way to describe this notation. So, but what it's basically saying is, like, if the plane has 100 seats and 80 people pay the lower fare, then there's 20 seats left over. So we would use 20. If the plane has 100 seats and 150 people wanted to buy those seats, well, we're going to sell the first 100 and then stop. So we don't want to say that there's minus 50 seats on the plane. That doesn't make sense. So if this number comes up negative, we just say it's 0 instead. So this plus means, basically means if this is negative, use 0. Otherwise, use the positive part. Maybe that's why they call it positive part. Okay. So now what the airlines do is a hybrid strategy of the two. They don't say we refuse to let the lower fare, any seats go with the lower fare, or they don't let them all go. So what we want to do is we want to basically say we'd like to protect And the textbooks on this topic use the letter Y. I wish they used a better letter, but they typically use the letter Y. So we're going to say we're going to protect Y units of sale for fare 1. So for example, like an airplane with 100 seats, we might say we're going to protect 60 for the higher paying people. So then, 30 days before the flight, we open up sales, and if maybe 40 people show up, then we sell the first 40 and then stop, and leave the last 60 seats for the higher fares. So our goal in the question is to pick the best value for Y. Okay, so if we said Y equals the capacity of the plane, that is the strategy before. That means we're protecting every seat. So we're only selling the high fare ones. If we say Y equals 0, then it's basically whoever shows up buys them. That's strategy 2 from before. Okay, but what we can do is we can allow Y to be any value between 0 and the size of the plane. And our goal is pick the best one. So therefore, capacity of the plane minus the ones that are being protected are available for fare 2. Whether they come and buy them all, we have to see. Okay, so what is the expected revenue for the flight? So the expected revenue, which a lot of textbooks use wealth, expected wealth and revenue. They kind of go back and forth. They always use W to mean expected revenue, but the W comes from wealth. So, okay. The expected wealth or revenue, using a plane with capacity C and picking the number Y, whatever the Y is, it would be the price to the lower fare, and then how many people show up. That would be, we see how many people naturally show up, that's demand 2, and then how many seats do we give to them? Well, that would be the capacity minus the amount we're saving for the higher fare. So whichever is the smaller of these two numbers, that's how many customers we have at the lower fare level. Multiply that by the lower price, that's how much money we'll make on the lower price. And then, the higher price, how many people will show up there? Well, that's going to be the demand, how many actually show up. And then, but we might get maxed out. We might not have that many seats available, so how many seats will that be? So now it's Y, the number we protected for them. So, like I said, it's maybe better following an example. Let's say we had a plane with 100 seats and Y was 60. So, a certain number of people show up, maybe 50, maybe 70, but it's going to be the number of seats we've protected, or it might be the capacity minus demand 2, if demand 2 was let more seats be available. So this would be the case where, let's say the capacity is 100, we protected 60 seats, but only 30 people showed up at level 2. Well, then that doesn't mean we have 60 seats available for level 1, we have now 70, because we just didn't get enough level 2 people. So, what this is trying to capture from here to here is how many seats are available for level 1. So that's going to be, we know for sure it's going to be at least 60, the amount we reserved. It might even be more if we didn't get enough of these customers. So it's going to be like, this means like 60 or more. And then we're taking the bigger of the two values. So that's how many empty seats there are available for the higher paying people, but if not enough of them show up, then it's going to be this number, not this number. So it's the maximum of these two numbers, Y and C minus D2, is the number of seats available, and then this is how many show up, and we take the minimum of those two numbers. And then we ask ourselves, what do we expect that to be? And then whatever that's expected to be times price 1, add that all up. So our goal is to maximize this value, this function. Basically, make this the best function, the one with the maximum value, and generally, but not always true, the capacity is fixed, like the airplane is however big.
The number of seats that's on the airplane.
Right, unless we can somehow, whatever the thing is we're selling, if there's some way we can make more, that would, like if we're making donuts rather than seats on a plane, we might be able to change this. But for the airplane example, this is fixed, and this is the one we can choose to change. So our goal is to pick the best Y for the airplane. So now, from a point of view of a marginal analysis, suppose suppose we decided y equals a particular number like 60 out of an airplane, and then a customer comes in. So let's say we sell the first 40 seats to the lower paying customers, and another customer shows up. Let's say it's 30 days before the flight's going to go out, and another customer shows up and says, "I'd like a seat," right? Now, if we think the whatever y we came up with is the best number, but what would make us sell this one extra seat? Like, we want to decide on a one more seat basis, should we or should we not sell this new person who's standing right in front of us with cash in their hands, ready to pay, because we don't know until, like, you know, a couple days before the flight if the higher paying business travelers are even going to come. But we know this person is standing right in front of us with money in their hand. So should we sell them the seat? So what would that be based on? Whether you would sell them or not sell it? So you know,
if you think that you may not fill the seats with higher price, then you may be willing to let one or two seats go at extra seats go at a lower price. That's one of the things that
if you think
of.
Right. If you think you may not sell it,
At a higher price.
if we do sell it, we'll get more money. If we don't sell it, then we're losing the person standing right in front of us with cash in their hand. So we want to ask ourselves, what has a better probability of happening? Collecting price 2, which is 100%, because the person's standing right in front of us, or collecting price 1, which may or may not happen. So the thing is, we would be if we say yes to the person and sell this one extra seat, we're going to collect price 2, like $299. And if we say no, what are we going to collect? Well, we might collect the higher price, $5.99, or we might collect 0 because no one shows up. So it's going to be $5.99, the higher price, times what is the probability that the demand, which is kind of a random variable, is bigger than or equal to the number we protected. Because we need, let's say we had y equals 60. We have to sell 60 seats just to get to the point where we've sold this person's seat, because it's kind of like the last one. So we have to ask ourselves, what is the probability that the demand 1 will beat or equal y? Then we would have sold this seat. And if it doesn't hit that number, even if it misses by 1, let's say only 59 people show up at the higher price, then we're letting an empty seat go out, and we should have let this seat go. We should have sold this seat, but we don't know the future. So it's going to be, this is going to be a probability thing that we don't control perfectly. Okay, so if we, let's see, if we answer yes, we should answer yes if price 2 is bigger than or equal to price 1 times the probability that that person shows up. Otherwise, we'd answer no. I guess this thing could be optional, right? Which, if they're equal, you could pick either one. So another way of looking at it is we have this ratio when price 2 over price 1 is less than, when this ratio is less than price 1 times the probability that it happens, then we would protect C units. So let me just go over an example like that. So this is kind of a famous result in dynamic pricing. It's called Littlewood's rule. So we're going to say that y subscript L is equal to the maximum of all the y's contained in this value where this ends up being true. Where this ratio, where the probability of the person showing up paying the higher price times the higher price beats the value of the lower price. Okay, so let's just go over this example. Now, as far as a probability distribution for people showing up at class 1 or class 2, before you see that this has Poisson on it, suppose we said that it was uniformly distributed. Does that seem like natural for people showing up for an airplane? So let's say, for example,
You mean like a normal distribution?
no, not normal distribution, that's another thing we could look at.
Okay.
But a uniform distribution means every probability has the same amount. So suppose
Okay.
we said, suppose we wanted to model, suppose we've been watching in the past how many people show up for different flights. Like maybe it's the same flight every day, New York to Chicago every day.
Historical data, you
Right.
look into that.
So we would know how many people showed up on a certain day. We might get like, we might get 80 one day and 85 the next day and 72 the next day. So random numbers. So if we wanted to model that, would we say like the number of people show up, it's between 0 and 200 and uniformly distributed, each number has the same exact chance? Does that seem, so uniform means every probability has the same chance, like rolling a dice. Every number has a 1/6 chance, so everything has the same chance. Normal distributed means it kind of follows a bell curve, and the average is in the middle of the bell.
Yeah.
So if you wanted to kind of model, what do you think is natural for an airplane flight? Like, does it seem like a uniform might make sense, or normal distributed? Like, would it be like from 1 to 200 with an average of, or let's say the average was 80, from 1 to 160 with an average of 80, like a bell curve? Does that seem normal, or does it seem more like there'd always be at least a certain amount and then it would taper off? Or
I think if you take the historical data, you can probably make it like a uniform. That way you know that there'll be a certain number of people who fly, as you said, between New York and Chicago in a weekday on business.
Oh,
Does that make-
well, I'm just saying, like, what does it seem like? So what we want to do, obviously, is we want to have a random way of, because we can't predict demand. So we'd like to somehow say, like, is it let's say on average, we could always figure out the average from past data, right? Just see how many people have been showing up in the past and take the average. We'll know what the average is, but what type of distribution should it be? Should it be like, yeah, uniform or a bell-shaped curve, or something that starts off big at the beginning and tapers off at the end? Like, is there a very high probability that you're going to get like between 50 and 90 people with an average of 80, but then it could be 110, 150, could be 500 at a very
low probability?
yeah, very low probability, but maybe tails off to infinity. So of all the famous distributions, you know, like normal distribution, uniform distribution, the Poisson distribution, which is named after a person named Poisson, the French mathematician, right? And it means, yeah, the name means fish in French, right?
Okay.
So, you ever seen that on a French menu? The fish section, the Poisson section?
No.
You know what I mean? Okay, that's the seafood section, but it actually
Okay.
means fish. So,
Oh, okay.
But, so it'd be like a person whose last name is Fish in
okay.
France.
In-
So,
okay.
okay. But anyway, so it's a famous distribution, but it's very natural in life. So it shows up, even like rolling a dice, if you phrase the question, as, when would I expect the first, 6 to come? If 6s come once every 6th roll, so the average would be 6, and then it turns out, like, the probability of the first 6, it's very likely to be near 6, but it could go way off, like it could be, the first one could be 100, but then it's very low probability.
Right.
But it kind of bunches up at the beginning and then tails off.
Okay.
So, so basically, any event that has an average, a Poisson distribution, in a very unofficial way of describing it, is any probability that has an average, but the average is kind of bunched up near the beginning of the average and then tapers off into the future. And the other important thing is that if the event doesn't happen on a, like, let's say on a particular roll of the dice, the next roll of the dice is independent of the past. So the Poisson probability is independent of its past.
Okay.
Okay, so let's say, so a good way of modeling how many people would show up on the flight would be to take the average over the past and then assume it's like a Poisson distribution. Might make a slight change to it to make it map perfectly to airplanes, but Poisson is a good distribution to use. So in this case, let's say we observe that 80%, I'm sorry, 80%, that we're going to use a Poisson distribution, and on average 80 people show up for the flight for the higher priced people. So now we could actually, with the Poisson distribution, we could pick a particular number and ask ourselves, what is the probability exactly that many people will show up? So if we notice the average is 80, we could say, well, what is the probability that exactly 75 people will show up? So the probability that D1 equals exactly 75 would be e to the negative 80 times 80 raised to the 75 divided by 75 factorial, and that comes out to, you know, some pretty small number. But then we could add up what is the probability that it's anywhere from 0 up to 80, and so on. Okay, now in this example we had price 1 is 100, price 2 is 60. So our ratio is now 60 divided by 100, which is 0.6. And then we ask ourselves, for what y, what value of y would demand 1, what value of y would demand 1 give us a value of 78, meaning the probability of, this ratio is the lower price divided by the higher price. We want to know what value of y will give us the probability that this formula, the probability that the demand would be, the demand times this price would be higher than that ratio. So for the value of 78, then it would, up to the value of 78, it would make sense for us to take the money from the lower paying one and then stop. So it ends up being that y, the best value for y would end up being 78. In the case where we're using the Poisson distribution and we've observed in the past an average of 80, this is what we expect to come up for the higher price demand, and then we would use a y of 78. So that would mean if the capacity of the plane was 100, we would allow 22 units to book. If the capacity was 50, we would still protect 78, and that would eat up the whole plane. So, so even if now if the capacity went to some bigger number, we would just protect the bigger number minus whatever it takes to get down to 78. Okay. Oh, sorry. And then here's an example of MATLAB code that would solve a slightly different problem. So in MATLAB, and I think, yeah, this is the midterm question, right? Okay, so I think so the question on the midterm was kind of like, it gives you this code and asks you some questions about it, and then asks you to, you know, solve a different problem.
Change, yeah.
Okay, so I think one of the questions was, what is clear all? Was that?
Yeah, that was one of the questions.
So that's a MATLAB thing. That just says clear all variables.
Correct.
And the reason why they do that is, if you said, if for some reason you said capacity is 100, and then later on down here you said, let me make capacity 200, and then you ran it, if you then saw the result and then ran it again, it could, well, this line would change it back to 100, but if this said like capacity is whatever capacity is plus 100, then it would be the value left off from the last time you run. So clear all means just take all variables and set them to whatever their default is. So for integers, that would be 0.
Right.
So basically it sets everything to 0. Okay. So we have a capacity of 100. We've decided to protect 60 seats. And now we've decided to let lambda, so I'm using Poisson, yeah. So we've decided to lambda, the Greek letter lambda is usually the popular letter to use for the average. Yeah. So we decided to let lambda 1 be 40, and then the higher price is $499, the lower price is $99. And then we're using a for loop in programming. That would mean we're going to do what's in this area, we're going to do that for every value of I between 1 and 100. Okay, so now what we're doing is we're saying demand 2, did the question, I mean, I know what this is doing, but okay. Demand 2 is going to be the minimum, so we're going to use the MATLAB function min, which actually can take an array of numbers and just tells you what the smallest one is. So we're going to take the minimum of 75, or the capacity minus the protected. So capacity is 100 minus protected, which is 60. So this is going to be 40.
Yeah.
But it looks like it's being set up so we can kind of play around with this number.
Yeah.
So we want to like leave this formula in. So this is basically saying I'm going to take the minimum of 75 and 40. Which
So
would,
what's the 75?
okay, so that's what caused me to hesitate for a second. And I think maybe the reason I did this was this should have. Let's think about that. So right now it's saying this is 75. Like. This is 75, and this is going to be based on the size of the plane and the number you pick.
Yeah.
And our goal is to pick the best number for here. So our goal is to keep changing this till we get the perfect number.
Correct.
The way we did it last time was, yeah. So actually, is there a question about this that says? How many people will show up at price level 2?
It says how many people will show up at, no, it says, one of the questions is if 70 people are willing to pay the high price, how many will we sell? That's one of the questions.
If 70 people are willing to pay, okay. So what it looks like here, this is, maybe it never asked this on the question. It looks like 75 people will show up looking to pay the lower price. And depending on if you have 75 seats or not, you'll sell up to that number. So what normally might make sense is we might have a different Poisson distribution that brings in more people here. But it looks like, you know, some strange world where exactly 75 people show up looking to pay the lower price. And if you have enough seats available, we'll sell them all. We'll sell the whole 75. Or if you don't have 75 seats, we'll sell however many seats you have. Then the demand for the first one, this looks a little bit more normal. So there might be, was there a follow-up question that says, assume that the number of people showing up at level 2 is Poisson distributed with a higher parameter?
Yeah.
Okay.
I think the next question was, change the demand rate of the lower paying customers to Poisson with lambda is 60.
Oh, okay. So you would change the 75. So instead of exactly 75 people showing up all the time, which is not natural in the real world, you would change the 75 to Poisson and then a lambda 2, and you'd have to make like a lambda 2 of 60. So anyway, what this code looks like it's doing is that this is in a world where they know exactly 75 people are going to show up looking to pay level 2 price. You may or may not have enough seats for them, and you'll take the smaller of those two numbers. And that's demand 2. So now the other thing is these are arrays. So this is an array of numbers that goes from 1 to 100. So we're going to have like a demand 2, and it's going to be 1, 2, 3, you know, all the way up to 100. So we're going to make we're going to artificially say that we have 100 different demands at level 2. Now in this case, it's going to be 100 minus 60. It's going to be an array that says 40, 40, 40, 40, up to 100. Then demand 1 is going to be, we're going to take a Poisson random variable, so this is a function in MATLAB. All you have to do is give it an average. All you have to do is give it a lambda, and then it'll kind of like roll, you know, simulate rolling a dice for you.
Okay.
And it'll give you a number, and we're going to take either that number or the capacity minus all the seats we gave to the lower paying, whichever is smaller of those two. And that's how many, that'll be the official demand. This actually should be, maybe they should call this satisfied demand, because it's not the demand, it's the demand, but we might not have enough seats for everybody, so it's
Correct.
the demand that got satisfied might be better names for these. So, okay, and then, so now what we have is two arrays that have two demands, demands that were actually sold, tickets that were actually sold. And now our total revenue is going to be price 2 times demand 2 plus price 1 times demand 1. And then just add that up. So now we have, like, as if we simulated the plane running 100 times, and then we take an average. We take what is the mean of the vector or the array of averages. So we have 100 revenues, like as if the plane went 100 times, and we're just taking the average.
Okay.
So, so like, what was some of the questions on?
One was
So the first
how
one,
much, sorry.
so the one was change the demand for 2, instead of being exactly 75 people showing up. Change it to Poisson with, what is this?
Lambda is 60.
Okay, so to solve that one, you would say lambda, you'd make it, you know, a new line. Lambda 2 equals 60, and then change the 75 to say Poisson lambda 2.
Okay,
So now a random number of people with an average of 60
correct.
will be showing up, and then maybe you'll sell that many seats, or you're only allowing 40. So if the number is greater than 40, you'll be selling 40, and if it's less than 40, you'll be selling however many showed up.
So the other variable would still be capacity minus protected?
Yeah.
Number of, okay.
So that's always like, so whenever we decide, like there's 100 seats on the plane, and we're gonna let 60 go to the higher paying customers, that means we're allowing, doesn't mean we're definitely gonna sell them, but we're allowing 40 seats.
Yeah.
And then, so if more than 40 or more people show up, we sell them all. If less, then we sell less, and we have extras for the higher paying ones.
Correct. The other question was, find the best value for protected if
Okay.
you change the demand to, as lambda is 60.
Okay. So you've already, so one part is to change this to Poisson 60.
And after you change it, you're asking what would be the best value for protected.
Okay.
So that would change as well when you change demand 2, would the value of protected change as well?
Well, okay, so so one part is to change the 75 to Poisson 60.
60.
Okay. Then the other one is saying now, like kind of, I'm giving you 60 as like a starting point, but
Okay.
maybe 59 is better, or maybe 61 is better.
Okay.
So first of all, was there a part that said
Change it to, yeah, 10,000.
a big one, right?
Yeah.
So 100 is not a good number of experiments because there's too much room for error. But
Yeah.
maybe change it to 1,000 or 10,000.
10,000, yeah.
Yeah, 10,000 might take like not a long time, but maybe like 10 seconds to do. So maybe change it to 1,000, try it, get a good answer, and then change it to 10,000.
Okay.
But anyway, so one thing you could do is you could run it,
Yeah.
and it'll give you an average.
Yeah.
Then maybe you could start doing marginal analysis. Make this a 59 and see if it comes out better.
Okay.
Make it a 61, see if it comes.
Okay.
So you could kind of alter this.
Play around and. Okay.
Right. There's also a programming way to do it where you would have you don't really have to do this, but it could save you a little time. If you look up a while loop, so you're basically starting with a guess, like 60.
Yeah.
And then you might say, let me run the experiment, see what the answer is.
Yeah.
And then I'm going to add, well, no, let's say you started with 0. So if you protected 0, that means as many people show up at
For
the
the
lower
lower
fare
price.
could buy it. Figure out what that answer is, and then maybe add 10 to that. Then make the variable protected, change it to whatever it currently is plus 10. If that gives you a better answer, add another 10.
Okay.
If that gives you, and keep doing it until you get a worse answer.
Correct.
Then you might say subtract 5, and keep subtracting 5 till it gets better, and then add 2.5. Like make the amount you add,
Yeah.
subtract, keep going until eventually there's no change in it.
Correct.
And just let it run, and that'll calculate it for you. But you
Okay.
can kind of do it manually by just running this, then maybe change this to 50. If that makes it worse, try 70. and just keep changing till you
Yeah,
get the best
okay.
answer, so.
Okay.
Okay. So, yeah, so, what, any
And
other?
the other one which I wasn't sure of was, it says, with what probability distribution and what mean do the higher paying customers arrive? So the mean would be
Oh,
the
that must have been
the
an
lambda?
earlier question, right? Yeah, so for the Poisson distribution,
Yeah,
so it basically has that kind of, the distribution starting at 0, it kind of goes up towards the average and then tapers off out to infinity.
okay,
And so the average is lambda.
okay.
What was the other part of the question?
With what probability distribution and
Okay.
what mean?
Yeah, so it's Poisson with 60.
Oh, the probability distribution is Poisson, and then the lambda would be 60
Right.
for higher paying.
For the high paying, because
Yeah.
that was for 1.
Correct.
Class
And for the
1.
lower paying, it would be,
Yeah, so this is kind of weird, but it would be 70, the mean would be
75 because
75,
you, okay,
and there's no distribution, it's 75.
yeah, okay,
So it's all the way 75.
okay,
Yeah, this is kind of odd looking, and then it's for you to take that and change it to
Correct,
something not so
correct.
odd looking.
yeah,
So, okay. So yeah, this is some world where exactly, like the same 75 people keep showing up every day,
okay,
something
yeah,
like that.
yeah.
But that's not natural, so.
And it says if 70 people are willing to pay the high price, how many will we sell? So for that, do you have to change protected to 70 and see what the answer is?
Wait, I'm sorry, if 70 people are willing to pay
At
the
the
high
high
price?
price, how many will we sell? So does that mean you're changing protected to 70 or you are,
It says if 70 people are willing, like we know that in advance?
that's one of the questions, yeah. It's like an example that you have given. It says if 70 people are willing to pay the high price. So if you know that in advance, yeah, you're
Okay,
right.
yeah. So
So
if
what-
somehow you knew in advance there would be
Correct.
70, then you might
Uh-huh.
as well let 30 go to the, you know you're gonna sell exactly 70
Okay.
for some,
Oh, okay, I got it.
then you might as well let as many up to 30
To,
go with
for
the
the
old
lower
price.
price, yeah.
Yeah,
Okay.
okay.